Hello, good morning. Sorry for the delay. I decided, I don't know, 10 minutes ago to change this class. So we're going to do a different topic. We're originally going to do linked data, but I think it makes a lot more sense in this order. So that's the reason why. So the slides are available online now as well. So we're going to talk about shapes and what are shapes. In the context of the course, we've spoken about data, logic, and queries. There's one element that is not on this slide that is also very useful, very important for the semantic web, which is the notion of shapes. So essentially, shapes are related to data quality. Yeah. So what shapes allow us to do essentially is to provide a schema. So at the start of the course, we argued a bit about the benefits of graph data, and we said a great thing about graph data is that we don't have to impose a schema or structure from the start. However, one of the disadvantages, of course, is that we don't have a structure or schema imposed from the start. And then we said how graphs still have this organic structure that can emerge over time. So what if we could have this option of flexibility of not imposing a structure or schema from the start, but also have a schema, which is to say that we don't need a schema, but if we want a schema, we can impose that at any time. So that's the notion of shapes. Shapes allow us to define a validating schema, not like RDF schema, it's quite different. I wouldn't even say RDF schema is really a schema language. So the question is, how can we impose a schema for graphs? What sort of stuff should we put in there? So there was a working group that were working on this, and they decided to try and maybe define some sort of schema for graphs that could be used to validate and to check the quality of data. So that's the idea of shapes. Shapes are used to validate the data. So here we have an RDF graph, and we're describing a movie, Parasite, that was released in 2020, and it won an Academy Award, basically. We see some information about the director, we see some information about the award, and another award here. So it won Academy Best Picture and Academy Best Director. Okay, so the question now is this graph complete, in quotes? Yeah. Is there some information missing from this? Does it have some errors? Are there some modeling problems? How do we define completeness and errors? Yeah. So the idea is that there's no global one answer to these questions, but within the context of a specific application, we can define some shapes that will allow us to specify what we need for that application. So we have what's called a shapes graph. A shapes graph is effectively describes a set of constraints on specific types of elements in our graph. Yeah. So if it looks a little bit like UML, that's not a coincidence. It sort of is UML. And we have some connections between these UML boxes. Yeah. So we have a box that refers to award, and it says, okay, an award has a year, and this year should be an XSDG year, Gregorian year, and it should have between 1 and 1 value. Sorry if it's a little difficult to see, but maybe you can open the slides. And then we have names. So we have name should have a language string. So the award should have a name in a particular language. Yeah, should be in English or Spanish or what have you. We then have some connections. So we say that an award has a judge, and it has 0 to many judges, and these judges must conform to the person shape. Yeah, so we have some sort of references between elements. So we have a bunch more information that we'll see. We also have some inheritance, which says that Academy Award is a specific type of award, and therefore it inherits the constraints of award. Okay. So now we have this graph here, and the question is, does this graph, this RDF graph, conform to this shapes graph here? That's the question. And if we look at it closely, well, there's something we're missing, right? So the first thing we're missing is, if we ask, does this RDF graph conform to the shapes graph? What we're missing currently is some idea of what elements of our shapes graph conforms to what elements of our RDF graph. Yeah. So essentially we have, for example, an award. Should we apply the award constraint to Parasite? Should we apply it to Bong Joon-ho? Should we apply it to Academy Best Director? Should we apply it to Academy Best Director 2020? What nodes do we apply the shapes constraints to? So does it pass? Currently it passes. It passes trivially because we haven't defined the target. What is the target? The target tells us the target of this constraint box here, this UML thing, these constraints are these nodes or these elements of the graph. We have not formed a connection between the shape graph and the RDF graph. So it passes because we've not yet defined a target, so we don't know which shape applies to which node in the data. So we need to define a third element, which is a target. So what is a target? A target basically tells us, gives us some information about this shape's element here. It targets certain nodes in the graph. Yeah, and one way to do that is to name all the nodes as targets, but that's obviously not very convenient if we have a very large graph. So there's different ways of doing targets, which we'll talk about a little bit later. So the first type of target that we can say, for example, that movie targets all nodes of type movie. So this says movie targets type movie. Yeah. So if we look at our RDF graph again, we see that we have parasite type movie. So now we know that this constraint must apply to this node here. Yep. And then we look at the constraints and we check. So it says, okay, year XSDG year. So a movie should have a year. That's of type 2 year. And here we see it does. It has 2019. So that's cool. Short, is it a short movie or not? Boolean 0 to 1. So an optional short attribute. We don't see any short here in parasite, but it's okay because it's 0 to 1. Yeah. And then we have name language string. So name language string 1 or more. So do we have at least one? Yes, we have a name. It's a language string. It has an English language. Yeah. So this looks good. Okay. So what's the next thing we need to look at? We also need to look at the reference shapes. So we have director 1 or more. That's a person. Yeah. So here from movie, we see that, okay, now parasite has a director. So that's good. But now this element has to conform to this shape here. Yeah. So what does it say? It says that this person, if to satisfy the person constraint, the person must have a name and a language string. And we see that the director doesn't. Yeah. Bong Joon-ho does not have, and apologies for the pronunciation in case. Maybe, I'm not sure. So they don't have a name. So he doesn't have a name in this graph, which means essentially that we're not going to pass. Yeah. So it's sufficient to find one problem to say that, okay, now this RDF graph doesn't pass the shapes graph. So no, parasite does not have a direct satisfying person. We're missing a name and the date of birth. Okay, so if we look at the second attribute here, it says date of birth 1 to 1, and we don't have a date of birth either for the director. Yeah. So this is the core idea of shapes, and there's numbers, there's different details and different features that we can describe for doing more complex constraints. So this is the core. Something moves. What's moving? Okay. Sorry. So any questions about this? Is that okay? So this is the core idea. Yeah. So we'll have to see how we define this later. Later, we're going to represent this in RDF, which is our nice data format. So we use that for not just the data, but the constraints. So then first thing we have is multiplicity. So we have this multiplicity here. Maybe just to clarify one point about multiplicity, what we're going to do here is we're going to change, we're going to say that a movie has 0 to more directors. Yeah. Now this creates a question. This creates a question about the semantics of the language that we need to define. Right. So we say movie has 0 or more directors that satisfy the shape person. Yeah. So now the question is, should this graph validate or not, according to the shapes? It should. So it's a question of semantics, right? It's a question of how we define the language. There's two options. We can say that if we define director 0 to more points to person, we can say that we only count the elements that satisfy the person shape, the directors that satisfy the person shape. That's one option. The second option is that we say that all of the directors have to satisfy the person shape, and there can be 0 to many of them. Yeah. So one could argue, and these sorts of debates are often had in working groups that design these languages about what's the best way to go. I'm not sure if you have any opinions on that. First one, second one. So in this case, the working group defined the second one. So even though it's 0 to many, all of the directors have to satisfy the person shape. Yeah. So even if they're, so it's not counting how many satisfy the person shape, it's saying that all of the directors have to satisfy the person shape, and there must be 0 to many of those. Yeah. So it's an important clarification. Okay, So in this case, we've added the name and the date of birth for the director. And now the question is, does it pass? So let's have a look and see. So we know that a movie, we know that it satisfies all this. We checked it before, and now we have a director 0 to many. So we have one director here. Director must satisfy the person shape. We have the language string, that looks good. We have the date of birth, that looks good. So from movie, we've managed to validate all of the elements. Yeah, we don't need to validate these other incoming elements. Yeah, we just go outwards from the constraint we have. Yeah. So what does it mean? It means that yes, we're good. So it looks like this validates this RDF graph now satisfies this shapes graph here. Okay. So a very common question people might ask is, why do we need shapes? Why don't we use RDFS? Why don't we use OWL? We saw cardinality, qualified cardinality, and in Sparkle we saw we could create queries to check for these sorts of problems. Yeah. So why do we need a new standard? We don't want to have unnecessary standards, right? It adds extra cost. So it is true that we could define something in RDFS in OWL that somehow is similar to what the shapes graph states. So we can say, for example, that an award, all of awards must have G year and property year. So all of their years are G years. We could say that it has a cardinality 1 on property year. So every award has 1 year and so forth. We can define a very similar type of constraint or in this case, they're not really constraints, but definitions as appear in the shapes graph. Yeah. The problem is that the semantics is very different between the two. So in this case, we're really defining this in the open world, and we're defining it without a unique name assumption. So what does that mean? It means basically that we can never check if there's data missing. We're going to infer that data if it's missing. So it's a very different semantics. In shapes, what we're trying to do is we're trying to validate the data to see if the data are complete. Yeah, we're not trying to reason about models and interpretation. So it's similar to what I said in Sparkle. In Sparkle, we count how many nodes are in a graph. In OWL, we count how many people are children of Vito, for example. Yeah. So this semantics is not ideal for us. So they are really two different purposes. Yeah, this is for inference and this is for validation of data. This is for inference within our data using model theoretic semantics, and this is for validating data to see if things are missing, for example. So shapes versus RDFS OWL, the difference is the semantics, the assumptions are different. So OWL assumes the open world assumption and no unique name assumption, and so we cannot easily detect missing data or duplicated values. Yeah. So for example, if we say that an award has a year, if our award in our data doesn't have a year under OWL, what happens? Nothing. We just understand that it must have a year and we don't know what that year is. And maybe that can be useful for inferring something. Whereas in Shackle, it says, no, there's an error here. We're expecting award to have a year. Okay, what about Sparkle? We can definitely do this in Sparkle. Yeah, we could do all this in Sparkle and it would be great, but the queries we have to do in Sparkle are super complicated and unintuitive. So what we want to do basically is we're trying to write a query in Sparkle that finds the constraint validations, the problems in the data. Yeah. So here we'll have, for example, a movie, and then we check to see if it has a year 1, and then we need to check to make sure it doesn't have multiple years, so we add year 2, and then we check to make sure that something is unbound or the data type is not incorrect and that they're not unequal. Yeah. So this is how we could check to make sure that something has exactly one. Each movie has exactly 1 year. That is XSDG year. Yeah. And writing this out, okay, it's given on the slide, but writing this out, even for like me, I have a lot of experience with Sparkle and so forth. It's a kind of a mind game of how to do this. Yeah, it's not easy. It's not trivial, and that's a relatively trivial constraint. So then we do something similar for short. We check short 1, short 2. We check to see if it's bound or unbound, if it's not equal, if it has the right data type, and so forth. So even a simple constraint to write it in Sparkle, you can do it, but it's very unintuitive to do. Yeah. So this is the reason why we have shapes. Yeah. So Sparkle, we can do it in Sparkle. It's got the correct semantics. We're operating on data. But it's difficult to express these types of constraints, even for people who have experience of Sparkle. Okay, questions, thoughts? All good. Okay, so we have a specific language that's been standardized in the semantic web called SHACL, or Shapes Constraint Language. So Shapes Constraint Language effectively allows us to define in a concrete syntax, which is actually RDF, an RDF-based vocabulary, shapes graphs. So essentially the question is, okay, we have this diagram here and we more or less understand what it's about, but how do we define shapes graphs? Yeah. So this is the Shapes Constraint Language, was recommended in 2017. There was a working group that started working on shapes, and there was some disagreement in the middle of the working group, and some people went off and defined SHACL, which became a recommendation, and others defined this other language called SHEX, which is very similar, but not based on RDF. But the one that was recommended was SHACL. So what is SHACL? SHACL is a way of defining shapes graphs effectively in RDF. So it provides a fixed vocabulary, which is this sh thing here, w3.org/ns/SHACL is the namespace used. So this namespace effectively gives a vocabulary for describing in RDF these shapes graphs. Yeah. So if we want to describe person, for example, in this shapes graph here, we say person a node shape, okay, something that targets nodes in the graph. And then we say it has some properties, yeah? So it has a property, which is the path name. So that we're defining here this restriction, name, RDF line string, 1 to 1 or more. Path name, data type, RDF line string, min count 1, yeah? So then we have a second property. We have property path date of birth, DOB, data type XSD date, min count 1, max count 1. So this gives us precisely 1 to 1. So the default, if we don't give a min count or a max count, is 0 to many. There's no constraint on it. So this is how we define these sorts of shapes in SHACL, yeah, in RDF syntax. So we can also reference node shapes, yeah. So in this case, we have movie, and movie has the year short name, so it has the same properties as before, similar kind of restrictions as we saw before. It also has this new one here, which is a little bit different. It has a path, which is director, and it says that the director value must satisfy the shape person. Yeah, so this is how we point from one shape to another. Yeah, so we have path director, node shape person, min count 1, and it states that must have at least one of these. So in this way, we can point from one node shape to another node shape. So now we're forming a graph. This forms the edges between the node shapes. Yeah. So the next thing we have are targets. So we specified the need for targets earlier. So if we want to say that movie target the class movie, so this will say that this shape movie will target all of the things that are an instance of movie in the RDF graph. Then we can use this target class property here. And this basically says that movie now targets all of the nodes of type movie. Yeah. So we need to distinguish these two things, and it's a very common mistake or kind of error in the lab. So we have a shape movie, which represents this thing here, which has S movie. It has a different IRI to the type itself. Yeah, this is an RDF type like we've seen in many of the other labs. So this is the identifier for the shape, and this is an identifier for the class that the shape identifies. You can mix them. Some people also say, oh, well, we can use the same IRI for both. I don't recommend it. I don't think it's a good practice. I think it's better to do it this way. So yeah, it's important to keep distinguished the type from the shape, yeah, the class from the shape. Okay, so we can also have inheritance, yeah. So in this case, what inheritance do we have? We have an award shape, and then we say an Academy Award inherits the constraints of award. It's a particular type of award, yeah. So how do we do this? Essentially, we have our award shape here, and we define the constraints we have here on year. We define the constraints on name. So we specify the data type and the cardinality, in this case, XSDG year, max count 1, min count 1, name, data type line string, min count 1. And then we would like to define the reference to person. Yeah? So we say property, path judge, node person. Yeah? So we say that an award has 0 to many judges that are, and all of those judges are people. Yeah, must satisfy the person shape. Okay, so what of these constraints applies to Academy Award? Essentially all of them. Yeah, we're going to say that Academy Award inherits all of those constraints. So how do we do this? When we define Academy Award, yeah, we assume now that we have already defined Person Movie Award. When we define Academy Award, we say that this is a node shape and that it applies all of the node constraints of award. So we just say node award. Yeah, and it says that anything that's in here must now satisfy also the award shape. Yeah, the award node shape node. Node shape. Sorry. So yeah, so now this inherits all of the constraints from award, plus it adds some new ones. It says that an Academy Award must have 0 to many nominated persons, must have 0 to many win persons, must have 0 to many or 1 to many nominated movies, and 1 to many win movies. So if we think of an Academy Award, some of them are won by movies directly. Yeah, like best movie. Yeah, so there's no person involved. So person is optional. And even if it's like a Academy Award Best Director, we're going to assume that we indicate the movie that won to the movie that the person directed. Yeah. So we're going to define movie as required, and we're going to define person as optional, as something that can be there or not. I actually don't know if there's been cases where multiple movies have won the same. Well, in this case, I guess, no, it has to be a year. Yeah. So I'm not sure if there's any instance of an Academy Award being won by multiple movies in the same year. Maybe there was, I don't remember when I designed this, but okay. We're going to assume here that it can be. Yeah, so an Academy Award in a single year can be won by multiple movies. For sure, they can be won by multiple people who were involved in costume design or music or what have you. Yeah, they share an award. Okay, so we've seen inheritance. We're going to inherit all of the award stuff, and then we're going to add these constraints for a nominated person, win person, nominated movie, and win movie. Yeah. Here we see what's interesting is we have no cardinality constraints. So what does this mean? It means that it's 0 to many by default. Yeah, if we don't specify a min count or a max count, then they simply don't apply. Okay, and then we continue with the inheritance. Then we can just say an Academy Best Picture applies the node of Academy Award, and Academy Best Director applies the node of Academy Award. Yeah, so we inherited all of the stuff from Academy Award and then recursively from award. Yeah. So if we wanted to, we could add as well some more constraints here. For example, we could say that Academy Best Picture has 0 nominations for person. Yeah. Oh, yeah. Best Picture has 0 nominations for person, but in this case, we haven't done that. Okay, so this is the overall structure of how we specify a shapes graph using Shackle. Yeah. Any questions or doubts? Okay, so we have to speak about a couple of features in the language that allow us to get more advanced constraints. Some of the options we have. So we previously mentioned the need for targets. So targets allow us to say which node shape targets which nodes in the graph, effectively. Yep. So it's not the only option. We saw a target using classes. Yeah. So where we target the instances of a class. We can also have target subjects of, which will target the domain of a property. For example, Wins movie. We can say the domain of Wins movie. We're going to target that. Yeah. We can target objects of, so we can target, for example, the range of a property. To say Wins movie, we want to target all of the objects of that, all of the things that have been won by movies. And we can target nodes, specific nodes. So this would obviously be kind of limited. If we have a very large graph and lots of nodes, it wouldn't be the most convenient, but maybe sometimes there are specific nodes that we want to specify constraints on. Yeah. So we can also name specific nodes that we want to target. Not so commonly used, but sometimes it can be used. Okay, so in this case, we have person, and we say that person is, rather than saying person is the class person, we're going to say person range win person. So anybody who is any element that is the object of win person, that is a value for win person, we're going to target that and say that they must satisfy the person constraint. Yep. So in this case, we add here the target person node shape, and we define the usual constraints we've seen here. and we say target objects of win person. Yeah, so this basically says that all the things that are value of win person, they must satisfy the person constraint. I'll give an example. Yeah. So if we look here, it's the only target we have. So we don't have this target movie anymore. So what we're going to do is apply the person constraint on this value of win person here. And we're going to check that the person has a name, which is a language string, and one or more. So this is fine. And has a date of birth, which is 1, and it's a type XSD date. So this looks good. So what do we conclude? Is it valid? It looks to be okay. Yeah, so it looks good. So we can target not just types, we can target ranges, domains, for specific nodes. An interesting feature of Shackle is that it has some limited integration of RDFS. So what would happen, for example, here, if we have a target class award, right? So we're going to assume that we're going to target award. And in our RDF graph, what happens if we have something that is, for example, an Academy Best Director or an Academy Best Picture? It's not directly an instance of award, but these are subclasses of Academy Award, and Academy Award is a subclass of award. Yeah. So in this case, we can infer that's an award, but it's not actually stated explicitly as being an award. So what happens in Shackle? Shackle allows for RDFS subclass reasoning. So it will do the subclass closure, but it only allows for that. So if we can infer the subclass through other means, like more complicated means like we saw in OWL, it doesn't help. But it will do for us the closure of RDFS subclass. Yeah, so we'll transitively find the subclasses. If we can infer the subclass through other means, again, it doesn't work. But if we have a path of subclass in the graph, then it will work for us. So what does it mean? It means actually that this award now does target these instances of more specific subclasses of award. So we will be targeting these instances here. Note that we don't actually target the classes. Yeah, we target the things that are instances of those classes. So we're not going to be targeting Academy Best Director, but rather, because that's a class, we're going to be targeting the instance, which is Academy Best Director 2020 of that class. Yeah. Okay. So it targets subclasses. So is this valid? Let's have a look. I'm not sure. We have year and name. We have to have precisely 1 year, which is a G year. And we have to have precisely one or more names that are language strings. So we need a year. Here we have a year, yes. And language string, a name. We don't have a name here, so it's already failed. Yeah. In this case, yeah, we also don't have a name. So we have a year, but we don't have a name. So in this case, it's not valid. Yeah, we're missing the names for the words. So these two nodes fail for not having a name. Yeah, and then after that, we'd also have to check the judge. If there is a judge, that it's a type person. Judge is optional, but in any case, there's no judge links, so that part is fine. So we're missing names is the main issue. Questions, doubts? Okay, so now we get to the fun part with all the tricky examples. So the next feature we have in Shackle are we can specify paths. So what we saw previously are fairly direct constraints where we just have a path that's a property. Yeah. So the question then is, why is it called path? Actually, the idea is that we can specify constraints not just directly on properties, but also on paths, things that are connected via paths, like in property paths in Sparkle. Yeah. So how does this work? We are going to define a language for paths in Shackle, which is based on property paths in Sparkle. Yeah. So we have to define these in RDF, which is a little bit annoying, but the syntax is relatively okay. So the first type of path we have is just a property. So we say a property like year. Yeah. So path year, and that just tells us specify something on the value of that property. We can specify something on the inverse of a property. And where I use E, this is the recursive definition. Yeah, so E could be something else that was defined before. Yeah. So E, for example, could be P, it could be another inverse or something that comes afterwards. Yeah. So we have the inverse of a path. Yeah. So in Sparkle notation, just so this is all Sparkle notation here, this is what it corresponds to in Sparkle property paths. we have E then F. Yeah, so E followed by F. So this would be, for example, we could have a property which could be parent. We could have inverse of parent, which would be like child. We could have E then F, parent followed by parent, which would be equivalent to grandparent. Yeah. E or F, we could have mother or father, which would be loosely equivalent to parent. We can have recursive E, which would be ancestors of somebody, and that would include themselves. So ancestors of Aidan, in this case, would include Aidan because the star includes the node itself. We have the plus, which is one or more, which would not include me if we ask for my ancestors. And then we have optional E. So, for example, a course or it's, well, that's not very interesting. A president and optionally the president that followed it. I can't think of a good example for optional. Yeah. So it's the node itself and as well as the any values it might have in a property. So we can define property paths. We can use property paths in Shackle with an RDF type syntax to define some more complex constraints. Yeah, so in this case, we have a shapes graph that just has two node shapes. It has Academy Best Director, which targets the type Academy Best Director. And we have Academy Award-winning Director. Yeah, so we have the specific node shape, which is targeting the directors that have won Academy Awards. So in this case, we're saying that Academy Best Director has Academy Best Director. On the path of win movie followed by director, it needs to satisfy the Academy Award-winning director shape. And the Academy Award-winning director shape must, in the inverse direction, satisfy win person. Yeah. Actually, I think now looking at that example, that's kind of a strange. This win person here is a bit strange because the director could have won other things that are not related to an Academy Award, but or Academy Best Director. But okay. So we're going to go with that. So we have here a path, which basically this is intuitively what this is saying is that if a movie wins Academy Best Director, then the director of that movie must satisfy the shape for people who've won Academy Awards or directors who've won Academy Awards. So how do we define this? Now, when we define our property, we define inner path, win movie, director, which means that we're not looking at the value of a property, but rather the values of things connected by a path. Yeah. A path of win movie followed by director. Here then we have path name, path date of birth, which are paths as we saw before. They're just simple properties. And here we have a path which is the inverse path of win person. So going in the other direction of win person again. Okay. So let's have a look at this graph and let's see if we satisfy the constraint or not. So the first thing is we have to start with our target, which is Academy Best Director. And it says, if you're an Academy Best Director, then we're going to target you. So this is ABD 2020. We have no internal constraints here. So what we need to check is that on the path of win movie followed by director, that it must satisfy this thing here. Yeah. So if we go win movie and then follow director, we get to Bong Joon-ho. Yeah. And then we say that this director here must satisfy this constraint. Yeah. Which is name language string one or more. So we have name language string, this is good. And we have one date of birth, that's a date. So that is good, okay. And in the inverse direction from win person, going back the win person edge here, we need to satisfy, this needs to satisfy Academy Best Director, which is recursive. Yeah, we see we actually get back to the same node and it's fine. Yeah. So essentially in this case, is it valid? Yes. So the key thing is that we can define constraints on things that are connected by paths, not just directly by simple properties. That's the key message here. Yeah, so we can specify paths, nodes that are reachable via paths with property paths, and then specify some node constraints on those. So that's a pretty cool feature. So this example is maybe a clearer example of when that is useful. So what we're going to define is a sequence of Academy Best Pictures. Yeah. So we're going to take one type of award and we're going to define a sequence of them using previous and next properties. Yeah. So what we're going to define essentially is that every Academy Best Picture must have on the path one or more previous star. Yeah. So what is previous star? this is essentially a path which says Academy Award, for example, 2002. Let's say we do Academy Award 2002 previous star. So Academy Award 2002 will be included, Academy Award 2001, Academy Award 2000, and so forth, all the way back to the first Academy Award. Yeah. So we're saying that each Academy Best Picture has one or more of these because it has at least itself. Yeah, even the first one has at least itself as previous star. Yeah. And then we're going to define inverse previous star, which is sort of like next. We're going to define that it has one or more of inverse previous star. Yeah, so that means even the last one will have itself as inverse previous star. And we define here the path. So the path here is this simple property here. The path previous star we see with path 0 or more path previous. And then the previous inverse star, we do path, we do 0 or more path, and then we do an inverse path previous. Yeah. So we define 0 or more of the inverse path. So we can compose these as these are recursive definitions. Yep. Okay, so now we have this this RDF graph here. We're targeting with this shape Academy Best Picture. We're targeting the things that are instance of Academy Best Picture. And we see that we have Academy Best Picture 1929, 1930, 1931, 1932, 1933. If I remember correctly, 1929 is the first year in which there was an Academy Award for Academy Awards in general, maybe, or Best Picture. So we're targeting all of these nodes. All of these nodes are targeted by this shape. Yeah. So the first thing what we're going to say is that it must be of type Academy Best Picture. Okay, well, that seems to be the case. All of these are of type Academy Best Picture. Year must have precisely one year. So we look at this and it must be a G year. We look at this. Each of them has exactly 1 year. Yep, that looks good. Now we need to look at this. So we need to check to see if every Academy Award that came previous to it satisfies this shape or not. Yeah. So we check here. Yeah, it seems to satisfy the shape, seems to satisfy the shape, seems to satisfy the shape, seems to satisfy the shape. So anything we can reach from a transitive chain of previous edges, all of these things seem to satisfy the shapes, so that's fine. And also in the other direction. So if we take this node, we need to check all of these nodes here to see if these satisfy the shape, and they all do. So we're good. Yeah. So valid, yes. So this allows us to check not just one award, but all of the awards that preceded it to make sure that they all satisfy the shape as we would expect. Yeah. So we can specify this path and then check the validity of the shapes. Okay. Any questions or doubts about that? We're good. We're getting there. So in terms of the constraints themselves, how they're specified. So here I'm going to use sigma as a shape, and then we're going to have E as a path. Yeah. So essentially, how we specify constraints in general, we specify a shape, and then we specify the constraints that apply according to that. Yeah. So if we have a node shape, then we specify the shape, and this will target nodes in N that satisfy the shape. N being the nodes of the graph. If we specify a property, we have to additionally specify a path. Yeah, so we specify a path because we're currently at some node, and then we need to reach some other nodes. Yeah, so in this case, we specify a path, and that gives us essentially all of the value nodes, all of the things we can reach via this path. Then we're going to be checking that they satisfy the shape effectively. Yeah. So one thing that's interesting is essentially node shape is like if we have the epsilon path. Yeah, so it's sort of like it just applies to the node itself. Whereas property, we can specify a path to traverse before we check the shape. So we've intuitively seen this before, I guess. Yeah, so when we apply a property, shape, what we're doing is we're specifying a path from the current nodes, and then the nodes we can reach from there, we apply the constraints to, we apply the shape to. Okay. So in this case, we're targeting all of these nodes here. Where's the target? Target class Academy Award. Yeah, so we're targeting all of these because they're of type Academy Best Picture, which is a subclass of Academy Award. And we're checking then the awards. We're checking the Academy Award. Yeah, so we're checking, this is referencing the node shape. So this applies directly to the nodes. And this is the award node shape. So we look at award and it says it must have a past year, which is G year. So we go from each note, we go to its year, and we check to make sure that the year is okay, which specifies that we must have at least one of them and they must be of G year. Yeah, so this looks okay. I think in every case, yeah, no. So this one fails. Yeah. So this one has no year. So we're going to fail that shape. And then we also specify that if the Academy Award wins a movie, the winning movie, must satisfy the node shape movie and must have at least one movie that won. So this has at least one movie that won. This one has no movie that won. This one has at least one movie that won. And then we need to check if the movie satisfies the movie shape. So we say that it has, if it has a year, it must be a data type. So in this case, this one fails because this is an integer. So that's not valid. In this case, we're okay. In this case, we're okay. In this case, we're not okay. I know we're okay as well because it's optional. So, okay, we have some failures. Yeah. So mainly we have this failure here and this failure here in terms of validation. Why are all of these failing? Let's have a look and see. Okay. So movie and node shape, property year, G year. Okay, so that's fine. Is there something that connects all of these things? Award and node shape. So this is the movies. Okay. So an award must have a year and must have a data type G year and must have a min count of 1. So this is okay, at least. Target class Academy Award, that's fine. Node award, that's fine. Property path win movie. At least one movie must have won. Okay. So if we go one by one, in this case, this one fails because it has no winning movie. Yeah. If we look in this case here, it fails because the movie that won doesn't have a G year as the year. Yeah, so this one fails. If we look at this one, it has no movie that won. This is what I missed before, I guess. So there's no winning movie, so that fails. We look at this one, it has a winning movie and it has a year, and the year is G year. But the movie must have a year, which it doesn't. So that one fails. No. Okay, sorry. So the movie, if it has a year, must be G year, but it doesn't have to have a year. We don't have a main count here, apologies. So in this case, this is okay. And previous, we have a win movie, but we don't have a year. So this one fails. Yeah. So in this case, fails because no movie, fails here because the year is an integer, fails because there's no movie, passes, everything is okay. And this one fails because it has no year. Yeah. So we have some, these are examples of constraints that are specified on specific properties or in specific shapes. We can have more complex constraints as well. We can specify more complex conditions that the graph must satisfy to be validated. So as you could imagine, one could specify Boolean constraints. So if we assume that we have all these shapes, then we can specify the negation of a shape, that something should not conform to a particular shape. We can specify the disjunction of a shape to say that something must satisfy one of these shapes. We can have a conjunction, which would specify that something must satisfy all of these shapes. And we can have an exclusive disjunction, which is like an XOR, which says that it must satisfy precisely one of the shapes in the list, yeah? Which is kind of a little bit unusual, but useful in certain circumstances. So in this case, we have Academy Best International Feature Film, which is a slightly unusual name. Because it basically is everywhere but the US, but I guess such is life. So we have Academy Award for Best International Feature Film. And what we're going to specify essentially is that it should not specify if there's a movie that wins, that movie cannot be from the US. So we're going to say that it does not satisfy the from US constraint. Yeah. So we're going to specify that it must satisfy the not from the US constraint and the feature movie shape. Yeah, so it must satisfy the feature movie shape and the not from US shape, or the not satisfy the from US shape. So here we have a bunch of Academy Best International Feature Films, and we need to check to see if we're going to satisfy, if these elements, these movies here, if they satisfy the shape or not. Yeah. So we say target class Academy best international feature film, which is this thing here. Then we say property path win movie. Okay, so we have win movie here. Yeah. And then we say that win movie must satisfy these two shapes, not from the US and feature movie. So what is from the US? It basically says that if you're from the US, you have the value US on country. Yeah. So we'll check each of these, and then the feature movie specifies that it has the value short, false. So it's not a short movie. So it's a feature length movie. Okay, it must have precisely one movie that is one. So let's have a look at each one. So we have this movie here, which wins, the movie that won it is Gentleman's Agreement. This says that it's a short, which is false, so that satisfies the feature movie, yeah. And it says that the country is the US. Yeah, is this a problem? Well, if the country is the US, it satisfies this constraint here, and we asked for it not to satisfy that constraint, yeah. So this one will fail, yeah, because it's from the US, it's not an international feature film. Yeah. So the next one, we have Mr. Vincent, and we have Mr. Vincent, country US, country France. Yeah. So we need to ask, does it satisfy the from US constraint? If it does, then it's a problem. We see that it just says that it has value US on country. This doesn't mean it can't have other values. So it's also going to be rejected. In this case, we have a movie, and this movie has no country. So therefore, if it has no country, it does not satisfy the US constraint, which is good. Yeah. So it's not from the US. We don't ask, I don't think anywhere specifically that it has a country. We just ask that it doesn't satisfy this, so that's okay. And we ask that it's a feature movie. So we ask that it has the value false for short. As you can see, I didn't put it because probably the graph would be non-planar. So in this case, it fails. Yeah. So it also fails. In this case, we have the 1950 movie Malpaga. That looks, I don't know, I wonder is that how it's correctly spelled, but okay. Malapaga. And then we have that Malapaga is a short, false, which is what we expect for feature movies. And the country is Italy. So we see that it does not satisfy the US constraint. It does satisfy the feature constraint, and therefore we can say that it is okay. Yeah. Sorry. This note here, yeah, the award won by Malapaga. What about the final one? What do we think? Will it pass or will it fail? This last one here. So does it satisfy the US constraint? So it's fine for that. Yeah, it doesn't satisfy US, which is what we want. Does it satisfy the feature film? No. So it's going to fail because it's not a short false. Yeah. So the last one also fails. Okay. So some of the constraints that we can specify that for every node n that's targeted by a shape, we can specify that it should be an instance of a particular class. We can specify, as we've seen many times, that it must have a particular data type. So if it has a year, that year must be XSDG year. And then it has a node kind. What is a node kind? This is referring to the types of RDF terms. So it should be a blank node, it should be an IRI, it should be a literal, it should be a literal or IRI, these sorts of combinations. Yeah. So we can specify these constraints on the types of values. Yeah. So in this case, we're targeting people, and we're going to say that we're going to target objects of one person. So we're targeting all the things again highlighted in pink here. We're going to say that the node kind should be blank node or IRI. So if we have a person, we shouldn't use a literal to represent them, basically. And then we specify that the data type for name should be a string, and it should be at least one. Okay, so let's go through one by one. Does Floyd pass here? Is Floyd okay? So Floyd passes the constraint that is blank node or IRI, so that's good. Yeah. What about the name? So name should be a string. There should be at least one of them. So name is a string. In this case, it fails. Yeah. Or does it? No, it passes. Sorry. It passes because, yeah, by default, this would be a string anyways. We don't need to specify explicitly that it's a string. Apologies. So in this case here, L milestone, does this person pass the constraint? So is it a blank note or an IRI? So it's an IRI, right? This is how we denote the IRIs in the syntax. So it's for the literals you usually use a square, and then for the blank notes it's usually a little underscore before. So it's an IRI, so that's okay. Does it have a name? It has a name. It has two names. Are all of the names of type string? Are all of the names of type string? In this case, no. There's one of them that's an int, and again, we're not counting how many satisfy. We're saying that all of the values have to satisfy that constraint. So in this case, it fails because it has a name that's not a string. Okay, Norman Parrock, does this satisfy the constraint of blank note or IRI? No, it's a literal directly, right? So in this case, the win person value we've given, instead of being an entity, we've given it just as a string, which is not correct. So this one fails. Franz Borsach, what do we think? So Franz Borsach is an IRI, so that's okay. Has two names. That's okay because we don't have a max count. And all of the names are strings, so that's okay. Yeah, so it seems like this should be fine. And Frank Lloyd, we see that Frank Lloyd has a name, which looks okay. It's a string, looks okay. Frank Lloyd is an IRI, so it should be fine. Yep. Oh, why? What did I miss? It's not a type person. Yeah. Cheers. So this the class here, we had to check for all of them as well if they're a type person. Yeah. So this one is, this one is, this one is, this one isn't. So it also fails not just for a literal, but Frank Lloyd should be specified to be in essence a person. Cheers. Yeah. So we missed this constraint. Okay. So we have some value range constraints that state for every node that it must have some sort of value, yeah, that has a maximum or a minimum value, yeah. For example, we can say that for the Academy Best Pictures, that the minimum possible value inclusive would be 1929, which is the first year in which the awards were placed, yeah. So we can specify a floor to say all of the values for Academy Award Best Picture, all of the years must be 1929 or after. So this would be using min inclusive, and we have max inclusive, and we have min exclusive and max exclusive as well. So in this case, we're going to require that all of the movies, all of the Academy Best Pictures, the awards themselves, have a year of at least 1929. So in this case, we see that it has a year that is 1929. So we say has G year, and this is the only constraint we're working with, right? Okay. So in this case, this seems pretty okay. This seems fine. 1930, what do we think? Is this okay or not? It's not okay, right? So a subtle issue is that this is specified as an integer. It's not given as a year. So this one fails. This one here, it says 0931, which is a valid G year, but it's too early. Yeah, so it seems to be a typo. So this one fails. This one here, 1932, seems to be fine. And this one here, Cavalcade, our Academy Best Picture in 1933, has no year. Yeah, is that a problem? No, it's not a problem because we've never specified here a mean count, minimum number. So this is fine. So this last one is fine. Okay, we can also specify, which we also saw earlier, and we kind of cheated and used one of these features earlier, which is we can specify that on a particular property shape, we can specify that it has a particular value, for example, the US, or we can specify that the value is in some list of options. Yeah. So in this case, we have, for example, a US movie would have the country has value, would have the value US for the path country. So in this case, we're checking US movie. We're saying it targets the object of win movie. So all the movies that win have to be from the US, which is very biased. We have here gentleman agreement. It has the country US, so that's fine. Mr. Vincent has the country US. It doesn't mean it can't have other values, so that's fine. Bicycle thief does not satisfy US movie, so that fails. Malapaga does not have the US as a country, so that fails. And Rashomon does not have US as a country, so that fits. Okay, we have some string-based constraints, so we can specify, for example, first of all, that a node is not a blank node, and then we can specify the minimum length of the string, the maximum length of the string, Or we can specify that a string matches a regular expression with some flags for case insensitivity and stuff like that. Yeah. So we can also specify this on IRIs if we want. So we can specify them on IRIs or literals, yeah, but not on blank notes, because blank notes, the labels don't really have any significance. So what are we specifying here? We're specifying that we're going to be targeting year. So we're going to be targeting directly notes that are literals in this case. We're going to require that they have the data type G year. We're going to require that they have a minimum length of 4 and a maximum length of 4, and that they satisfy the following pattern, which is a regular expression, which is that it has the string 19 or 20, followed by 0 to 9, followed by 0 to 9. So this would be 1926, 1927, 1954, 2092, all of these sorts of years satisfy this pattern. And then we add a flag, which is I, which is just case insensitivity. So we apply a case insensitivity just for this example. It actually does nothing here, right? Because we have numbers. So numbers are not case insensitive. The case doesn't matter. So let's check our values. So we're targeting the objects of year. So the objects of year are the things we have in pink again here. And we require that we satisfy that everything have the data type G year, and that it matches this regular expression here. So what do we think about this year? Is this okay? Yeah, so we have to ask, does it have the data type G year, which it does? Does it have a minimum length of 4, just counting the string itself? It does. Does it have a maximum length of 4? It does. Does it match this pattern here of 19 or 20 followed by 2 numbers? It does. So it's all good. Yeah. So this first one is fine. What about this year here? Do we think it passes? No, it doesn't pass because we have int rather than year. Yeah, so this one fails. What about this one here? Does this pass? We have G year, we have a string of length 4, but it doesn't pass because it doesn't match the regular expression. Yeah, so it doesn't start with 19 or 20. What about 1932? That looks fine. And that's it. Yeah, so these are all the notes that are targeted. What's interesting here that just want to highlight that is that we can also target literals directly. Yeah, so we can put the focus on literals and then specify node shapes for those literals. So some string-based constraints, we can also specify that if a node is a literal, that it has a language that matches a certain list of options. So we can say that the language must be, for example, in English or Spanish and so forth. So we can also have a unique language constraint that says that we don't have any duplicate names in a certain language. Yeah. So it either has no language tag, it has an empty language tag, or a language tag unique in name. So it means that basically we don't have duplicated English names for something. Yeah, that's the core intuition. So in this case, we're going to specify that the language must be in ES or EN. So we're expecting all of the names to be in Spanish or in English, and we're expecting the unique language property. So we're expecting no duplicate names in a particular language. Yeah. So here we have some examples. So we're asking in this case that property path name. So if something has a name, it must be English or Spanish, and it must be unique language. So just to mention, we'll come to that later, we'll see it in the example, but ES will also match the specific variant. So you've probably seen like ESCL or ENUS or UK, where we have this sort of hierarchical language codes. Yeah. So if we specify ES, it will also match variants. So what about the first movie here that one? Do we think that this will satisfy the constraint? It has no name. Is that a problem? So in this case, it's not a problem. Why not? There's no main count. Yeah, so no main count. We're not requiring that everything have a name. What about Mr. Vincent? We have Senor Vincent here and Mr. Vincent. One in Spanish, one in English. This is good. Yeah, this is good. So this is perfectly fine. We have here bicycle thieves. So bicycle thieves has this name here, and this name has no language. So intuitively, we would say, okay, this is a problem. Yeah, we expect the language to be English or Spanish. So if we don't specify it, essentially it's not a language tag ID. I guess one could argue that maybe, okay, this should be accepted, but in the semantics, this will not be accepted. We have Malapaga, and we have the name in Chilean Spanish of Malapaga, and we have Malapo. Okay, and we have two names in Spanish. Yeah, is this a problem? This is a problem. It does not specify, it does not match the unique language constraint. In this case, we have Rashomon and we have the name in Japanese. Is this a problem? It's a problem because Japanese is not in our list of language in. Yeah, so this one's also a problem. Okay, so we have some cardinality constraints as well. So given a path E, then we can specify how many values there are basically on that path. So we can specify a max count and a min count, which we've seen several times. And we specify that that affects the count no matter whether or not how many things satisfy the constraint. If we wanted to specify how many things satisfy a constraint, we can use a qualified min count or a qualified max count, and then that only counts the things that satisfy a constraint. Yeah, so we have that option as well. So in this case, we have an example where we have first in series a node shape, and we say that it has 0 previous elements in the series. Yeah, so the first thing in a series has nothing before it. There's no 0 previous elements. And then we say that Academy best picture on the property which is 0 or more path of previous, so recursively all the things that came previously, it must have precisely one node, so qualified max count 1, qualified min count 1 on the shape first in series. Yeah. So let's have a look at an example and see what that means for us. So it means that basically to satisfy the first in series shape, what we need to do is we need to have 0 previous elements. Yeah. So does this satisfy the first in series shape? Yeah. Does this one? No. Right. So now what we're saying is for every Academy best picture, what we'd like to have is that all of the things that recursively follow each element, that there's only one in that series that satisfies the first in series constraint. So there's only one thing in that chain of previous words that doesn't have a previous. Okay, so we'll check each of these nodes here. What about 1929? Is this one okay? So 1929, okay, so if we look at the path, it's 0 or more previous. So 1929 itself is on this path. And 1929 satisfies the first in series shape. It has no previous, yeah, so there's nothing before it. So in this case, it's okay. It has precisely one element that satisfies the first element in series. Yeah. Does that make sense? So from 1929, we can reach 1929 itself on a path of 0 or more previous, and it has no previous. So it has exactly one node that matches first in series. What about 1930? What do we think? So 1930 on the path of 0 or more previous, we can get to 1930 and 1929. And then we need to count for both of those. We need to look to see which one satisfies first in series. 1929 satisfies first in series. Does 1930, does it have a previous edge? So 1930 has a previous edge, which means that it does not satisfy first in series. Yeah, so if we count all of the things from 1930 in the path of previous that satisfy first in series, there's precisely one. So it's okay. Yeah. What about 1931? So 1931, from 1931, if we go back recursively along all the previous elements, we have 1930, we have 1929, we have 1931 itself because it's previous star, and we have this APB thing here. Yeah, we have this node here. So we see that we have some problem with the data here. So if we count now, we ask how many nodes on these paths, on this previous star path, satisfy first in series. We see that 1929 has no previous, so that's 1. And we see APB has no previous, so that's 2. Yeah. So it no longer satisfies the constraint. Yeah. So now 1931 here fails because it has 2 elements that appear to be the first in the series. This APB thing here and this 1929. If we do 1932, we end up with the same problem because we reach APB here and we reach 1929 here. There's a branch, so this also fails. And the same for 1933. Yeah, it will also fail because now there appears to be on the chain 2 things that are the first in the series. Questions or doubts? Oh, we're getting there. We're getting there. So we have a property pair constraint that allows for specifying equality, disjointness, or some inequality between values of two paths, or a path with a property, being more specific. So what does this mean? Let's take an example. We can say, for example, that the year that won a particular award that won in a particular year, we can specify that the award came after the movie. So the movie was released, let's say in 2019, the award would be 2020. That's quite okay. Yeah. If we have an award that was awarded to a movie that comes in the future, then that's a problem. So we can specify this, in this case, using less than. We can also specify that there's some disjointness with year, for example, where we specify that no award can have the same year as something that came before it. Yeah, so if this award is Academy Award Best Picture 1956, and it has the year 1956, we would expect no other movie recursively previous to it, or in the future, to have that same year. Yeah, so this specifies one or more paths, so it doesn't include the movie itself. And it says inverse path of previous, so we're going into the future, and one or more path previous, which goes into the past. Yeah, so it basically tells us that no past or present future, no past or future award in the same series should share the same year as the current award. Okay, so we can have a look here and see if we satisfy these constraints here. So the first thing we need to keep in mind is that the award was won after the movie was released, and that no awards in the sequence share the same year. So we have 1929. Okay, we have no win movie here, so that's not a problem. So 1929 is 1929. Does it share 1929 with any other movie? No. So this is okay. Yeah. Next, we have 1930, Academy Award for Best Picture in 1930. We have win movie, All Quiet, and we have year 1930. Yeah. So we have that the movie came out in the same year as the award. Is this a problem? It's a problem. Yeah. It's a problem because we specify less than. So we require that the movie came out before the award. So this would be an issue. So this one fails. What about 1931? 1931 has the year 1930. Yeah. And we require that no award would match with no award would have the same year as no other award in the sequence. So this award here and this award here, they share the same year. So this is a problem. So this one also fails. What about 1932? 1932 has this movie here, which is not shared anywhere else. So this one seems okay. And the movie here has no year, but it doesn't need a year, so this one's okay. And finally, we have this award here, which has a movie. It has no year. So there is no problem with this either. Yeah. So we don't require that the awards have movies. We just require that if it has a year, it doesn't share it with any other award in the sequence. And then if it has a year, it's after the movie was released that won the award. Okay, so we have this more general constraint as well, which are closed constraints, which specify that only properties in the shapes graph are allowed. So essentially, it basically says that if there isn't something mentioned in the shape, like a property mentioned in the shape, then the node should not have that defined. Yeah, so it allows you to say, and nothing else is defined aside from what's explicitly mentioned by the shape. We can also specify a list of ignored properties, properties that we don't include in this closed constraint. Yeah. So what does this mean? It means if we look at this example here, we have an Academy Award, which is a node shape. It targets the Academy Award instances. It specifies a property on a constraint on win movie. It specifies a constraint on year, and it ignores previous and RDF type, and it closes that. So it says basically that all of the targeted movies, they can have 4 properties. They can have win movie, because that's explicitly mentioned. They can have year, which is explicitly mentioned. They can have previous, which was ignored, and RDF type, which is also ignored or excluded from the closed constraint. So we need to check and make sure that every node satisfies this. So here we have year. Year is explicitly in the shape, so this is okay. We have this award here, which is year and win movie, and we have year and win movie here, so that's okay. Okay. Sorry. Okay, so we've not mentioned previous. It also has previous here, and previous is not mentioned here in the shape, and previous. Oh no, previous is here. The data type it doesn't specify, doesn't match the data type. Yeah, apologies. Thanks for that. So here it doesn't match the G year data type. So this one's broken. In this case here, we have previous, we have RDF type, and we have an incoming previous. The incoming doesn't matter, so we satisfy the close constraint, and we have no min count, so this should be fine. Here we have win movie year previous, so this is also okay. This satisfies the data type, should be fine. And here we have winner cavalcade. We have previous this thing, and so we have a problem, which is winner is not, it's a fresh property. It's not a property that's specified. The property in the shape is win movie. So we've just invented a new property that we can't use. So this one is invalid. Yeah. So this one does not match the close constraint, does not satisfy the close constraint. Okay, so this is the core, these are all of the core constraints in Shackle. To mention that there's also some stuff we could specify in Sparkle that are not really specifiable in Shackle. However, Shackle allows us to specify constraints in Sparkle as well. So the idea basically is that we can specify a Sparkle query that should return effectively violations of the constraint. Yeah, so we want to search for things that don't satisfy the constraint. Yeah, so this is a Sparkle constraint. We specify in this case a constraint which will return all of the elements that don't satisfy somehow that don't satisfy this constraint. So whatever we return is problematic here. In this case, what are we doing? We have a select query, and we're looking for this and year as path value. So this will be matched directly to the target node that's being examined at the moment. We're going to return here the target node year value, this win movie year movie, and then we're going to check if it's 1 year on from that or not. Okay? So if the year movie is not 1 year plus 1 year is not equal to the integer value of the year of the award, and integer the year of the movie is not equal to the year of the award. So basically we're saying that the year of the award should be either the same year as the movie or the year afterwards. Yeah. So if we go through this and we look, constraints will indicate constraint violations, and this will be replaced with target nodes. Yeah. So if we look at this, in this case here, we should be fine. We'll return nothing because it has no win movie. It doesn't satisfy this thing here, so no result is generated for this node here. So this should be fine. In this case, we have a win movie. We have a year, and we have a year for this movie as well, but they coincide. They're the same year. So this should also be fine. In this case, we have a year, but again, we have no win movie. So this should also be fine. In this case, we have a year and we have a win movie, and the year is 1933. So in this case, it doesn't make sense that the award was awarded to a movie that hasn't come out yet. Yeah. So in this case, we say that there's a problem. And in this case here, we see that it wins in 1933. Win movie is 1933. So this is fine, I guess, because it has no year. So it's not going to be returned by this. So this one's also fine. Okay. So we can specify constraints. If there's something in Shackle that we can't specify directly, we can use this Sparkle constraints. But just to mention again that this is really quite difficult. It's not an easy thing to write Sparkle queries to do these sorts of constraints. But you can do it in the language. You can do this in Shackle. So briefly at the start, I mentioned that there was maybe some disagreement within the working group, and there was this other shape expression, this other language for describing shapes. This is called Shex. So Shex is also not standardized, it's not recommended, but there is a community, there is some sort of specification for it. So there was a split in the people working on this, and some people went in this direction of defining Shex. So Shex is sort of similar, but the original version or syntax for Shex, excuse me, they decided that rather than using RDF, they would try to come up with a more concise language, and this was part of the disagreement. There's also some disagreement in terms of the semantics, and so you see the syntax here is not RDF, it's more like a pseudo kind of JSON kind of style syntax. There's also some other issues, like by default, if you don't specify a multiplicity, the default multiplicity is exactly 1, and there's some other minor differences or details. But Shex essentially is another way of defining these sorts of shape graphs here. Yeah, so there's this sort of competing language, and many tools will support both shackle and checks. Because once you've taken the syntax and parsed it into some sort of representation that's a shapes graph, it's all more or less the same how you run your validation later. So there are two syntaxes with some slightly different semantics for the similar thing. So as it happens, checks is used by Wikidata. Yes, so Wikidata, if you're looking through Wikidata at some point and you see a little exclamation mark, and that's usually associated with a warning, those warnings are generated by the sort of validation. Yeah. So in this case here, what we're specifying is that if I recall the P's, which I probably don't, that P31 would be an instance of, so we have an actor shape here, and it says that actors must have an instance that is human, so it must be an instance of human. P21 would be country, so it must have a country element. And that it, because by default, the dot means any value for country. Yeah. And then P106, I don't remember what P106 is. Profession, probably. So it must have, so profession, it can have 0 or many professions. Maybe I'm wrong with P106. Maybe it's not profession. And I guess a profession would be something like actor or actress or something like that. Yeah. So these sorts of shapes are used by Wikidata using the checks. The checks language rather than shackle. So this is shapes. We have some optional validating schema that we can use. So we have somehow the benefits of, we somehow address one of the main disadvantages of graphs, which is that we don't really have a schema or a structure that we impose. With shapes, we can have our graphs, and we can optionally at any time impose a schema using something like shapes, yeah, like shackle or checks. And we can use this to validate our data and make sure that our data are valid at every step of data processing pipeline, for example. So that's shapes, shackle. Any questions, doubts? Okay, so on Wednesday we'll have a lab, which will be an RDF playground, where we'll give you some data, and we'll ask you to define some shapes to validate those data. We have one more class left. This was the main reason why I wanted to change the order of the classes. The last class I can also combine with the conclusion, because they kind of have a similar point. So we can have we'll have our last class next Monday. I think this Friday is bank holiday, feriado. Yeah, okay. So we'll have our last class on lab pair next week. And then we'll move to projects. Yeah, so we'll have project sessions to advance our projects. Any questions, doubts? If not, see you on Wednesday. Cheers.